So the development length of the bar is given by LD is equal to phi into sigma s upon 4 tau BD, which we have already seen. Phi is the nominal diameter of the bar, sigma s is 0.87 Fy, that is a stress in the bar at the section considered at design load. Tau BD is the design bond stress. The table has been produced over here from IS 456 2000. It is given on page 42 and 43. The formula is there on page number 42 of the code. The table exists on page 43 of the code. Now if you observe over here, for various grades of concrete, please note, for various grades of concrete, the design bond stress has been given, because bond stress is directly related to the type of concrete. So for M20, the amount of bond stress is 1.2, M25 it is 1.4, for M30 the bond stress, the design bond stress is 1.5 Newton per mm square, for M35 1.7 Newton per mm square, and please note over here, for all the other concretes above M40 it is 1.9 itself. 1.9 Newton per mm square is the design bond stress. This is what has been given in IS 456 2000. So over here, another important thing which has been mentioned, which I would like to stress, is that development length LD includes the anchorage values of hooks in tension reinforcement. Whatever hooks we provide, that also is considered in LD. It also says that for non-circular bars, the development length, the calculated development length should be sufficient to develop stress in bar by bond. So we need to be careful about these things whenever we are using any bar which is not circular in nature. Hooks and bends. Now whenever we are talking of hooks and bends, what are the standard hooks and bends? Now as per IS 456, a hook is the one which has the shape, that is, this is the reinforcement bar, it is turned back. Now what is this turned back? Why is this called as a hook? It looks like a hook. Okay, we can say a fishing hook or a hook. Okay, it looks like a hook. Now how much is the angle by which this has been turned? Look at this. The bar would have continued to be straight over here. The bar originally was straight over here. This bar has been bent at right angles first. This bar has been bent at right angles first and then turned like this. So one right angle here and then another right angle here. So total angle by which the bar has been bent is 180 degrees. So a hook is also known as 180 degree bend. So the bar which is straight originally, is bent into right angle first and then another right angle. So right angle and right angle gives me 180 degrees. So a standard hook is a bar bent by 180 degrees. Now this is a bend. This is a 90 degree bend which I was just talking about over here. The bar which is straight is bent at right angle. So the angle made over here, it is always the angle made over here, the external angle, the deflection angle which we understand it as. The bar makes a deflection angle of 90 degrees over here. So that's the bar, that's the standard 90 degree bend over here. So 90 degree bend and a hook. So standard hook and standard bend over here. Now there are anchorage values of hooks and bends given in the IS code. What are the anchorage values? Now the anchorage value, whenever we have a hook like this or whenever we have a bend like this, how much is the value to be taken for anchorage? Now the anchorage value of a hook for a 6 mm bar is 9.6, 8 mm bar is 12.8, 10 mm bar is 16, and so on and so on. Now anchorage value of a 90 degree bend is, for the same 6 mm bar, look at this, it is half of a hook. For 8 it is half of this, half of this, and so on. So the bend has half the value of the hook. The bend has half the value of hook as the anchorage value. Please note the band over here, 90-degree band. This is a 90-degree band and this is a 180-degree band or a hook. This has greater anchorage value than this. Now how many different types of bends can be there? The bends can be right angle, it can be at 45 degrees, it can be at 135 degrees. Normally the bends which are done, the bends which are provided have angles in multiples of 45 degrees. So this is 2 times 45 degrees, which is 90 degrees. We can have 45 degrees over here, or we can have this band like this, which makes the external angle, the deflection angle, as 135 degrees. Over here we have 180 degrees. Please note, for the standard hook and band, for the type of steel, this, how much is the radius of this? Minimum value of K for mild steel is 2, so this can be 2 times the diameter, and for cold steel bars it is 4 times the diameter. Please note, this is 4 times the diameter. Now development length. Now as per the explanatory code, now these things have been taken from the explanatory code of IS 456. That explanatory code is SP24 1983. Now in this, it says that the development length may be changed, may be reduced, if the amount of steel provided is larger than the amount required from the design process. Suppose in the design process I require amount of steel as 200, but what has been provided over there, because the bar diameter is available or because of whatever reason, is 400. That means for a design point of view I require 200, but what I have provided is 400. In that case, we understand that the stress coming in the bar, would be much reduced because much more steel is available over there. So the stress in the bar would be reduced. So what does the code say? In the formula for the development length, the appropriate values for sigma s and tau bd are to be used depending upon the method of design adopted. There is no change as far as that part is concerned, that is sigma s and tau bd. So alternately, what is done is, if the amount of steel provided at a section is more than that required from design considerations, the development length may be modified as AS required upon AS provided into what was calculated earlier. Okay, the values of the development length obtained for the two methods of design may not coincide, but we will be approximately equal. Now in this case, what I had said is AS required was 200, but what was provided is 400. So this becomes 1 upon 2. In that case, this LD required, LD modified required would be the original LD divided by 2. This is what has been told in SP24 1983. So we can actually reduce the development length by increasing the amount of steel provided from design considerations. Now anchoring reinforcing bar. This is the most important topic, anchoring the reinforcing bars. The real performance of bond in compression is not precisely known. In compression, how it works is not known at all. The present practice of understanding bond in compression is based on the consideration that behavior is similar to how it behaves in tension. But in tension, there are tension cracks which are developed. But in compression, there are no tension cracks developed. So therefore, the development length required is obviously shorter for bars in compression than in tension, because those cracks are not developed which are getting developed in tension. In compression, those cracks don't get developed. So that's why we can provide lesser development length in compression. Therefore, the values of bond stress in tension are, therefore whenever we are calculating the development length in compression, the bond stress value which is given in tension is increased by 25%. The stress is increased by 25%, so the amount of length which we get, which is required in compression, is lesser by 25%. Also, which we need to understand over here is that the code says in 25.2.2.1, any deficiency in the required development length can be made up by anchoring the reinforcing bar suitably. So If we can provide hooks and bands, it is fine. If we cannot provide hooks and bands, we can use anchors also. That is what has been told over here. Now please note one thing very important over here. The deformed bars have superior bond properties owing to mechanical bearing, which we have already discussed earlier. The projections which are there present in the deformed bars, they help in bond, they help in anchoring the bar. That's why the code says provision of hooks is not as absolutely essential as far as deformed bars is concerned. As far as deformed bars is concerned, we may not provide the hooks. That is what exactly what the code says. But in plain bars, the end hooks are necessary. Okay, end hooks have to be given for total mobilization of strength, bond strength. Now that mobilization of bond strength would be through adhesion also and through friction also. Now for deformed bars, these values are increased by 60%. The value of the bond stress is increased by 60%. That means in deformed bars, the total development length required would be 60% lesser than that in the plain bars. Coming to compression bars, which we have already discussed earlier, for bars in compression, the values of bond stress for bars in tension shall be increased by 25%. So over here also, in compression, the value of the development length, will be coming will be coming about 25% lesser. That is exactly what has been mentioned over here. So that's how we allow for hooks and bends. Now what are the values over here? Some very important thing which we need to know about this hooks and bends. The deformed bars may be used without end anchorages, which has been already told. Hooks should normally be provided for plain bars in tension. That also we have seen. Now this is a very important clause over here that is given in clause 26.2.1 2.2. Bends and hooks shall conform to IS 2502, that is IS code for bends and hooks. Now what are the anchorage values? For bends, the anchorage value of bend shall be taken as 4 times the diameter for each 45-degree bend. Each 45-degree bend, the value will be taken as 4 times the diameter, 4D. So that means if we are having a bend which is 90 degree, which we have seen earlier, a bend which is 90 degree is 90 is 2 times 45. For each 45, we are taking the anchorage value as 4 times diameter. So that means 2 times 2 of 45, that means 2 times 4D. That means for a right angle, we will be taking it as 8 times the diameter. Please note, please try to understand this part. The anchorage value is taken as 4 times the diameter for each 45 degrees. In a 90 degrees, there are 245 degrees. Per 45 degrees, it is 4 times the diameter. Since it is 2 times 45 degrees, it is going to be 8 times the diameter. So anchorage value of a 90 degree bend will be 8 times diameter. Similarly, the anchorage value of a standard U-type hook, that is 180 degree band, shall be 16 times the diameter. Now why 16 times? As we have said, a U hook is 180 degrees. So 45 into 4 becomes 180 degrees. So now the value of 4 times the diameter will have to be taken 4 times. So 4 times the diameter, 4 times becomes 16 times diameter. So that is what we observe over here. Anchorage value of hook will be taken as 16 times the diameter, and that of a band will be taken as 8 times the diameter. That's why a 90 degree band is having anchorage value half of that of a hook. Look at this. Anchorage value of a hook, look at only 10 mm diameter. When I look at 10 mm diameter, it is 16 into 10 as per this. 16 into 10 becomes 160 mm or 16 centimeters. For a hook, it is 160 mm or 16 centimeters. Anchorage value of a 90 degree band for 10 diameter bar, 10 mm diameter bar is 8 times the diameter. 8 into 10 becomes 80, that is 8 centimeters. That has been given over here as 8 centimeters. So similarly for 12 mm bars, 16 mm bars, and so on. Look at 20 mm bars. This is 16 times and this is 8 times. So that's how we calculate the anchorage value. So whenever we are providing the anchorages, how much anchorage is required, we calculate based on the hook this much anchorage already provided. Rest of the length has to be provided. Suppose I'm required to provide somewhere around 500 mm and I have provided a hook, then 16 times the diameter is already taken as part of the anchorage of the hook. The balance of the reinforcement we have to provide over there. So this is the way how we provide the development length.